nothing beats this video. We are going to come up with the infamous chain rule. So we want to figure out what this rule is, and then after we establish it in the next video, we'll look at some examples of how to use it. But this video will be focused on what it is. So here is our goal for this video, and that is to come up with the derivative with respect to x of a function of the form f of g of x. So of course that is a composite function. And just as a refresher, remember that we can also write it this way over here, f of g of x, that little open circle looking symbol, that is the same as the composite notation, and these mean the same thing. So the goal here is to find the derivative with respect to x of a composite function of the form f of g of x. That's our goal. Let's start off by kind of getting a feel about maybe how this works by considering a function that is a composite function here, this function h of x that we see on our screen, which is the function quantity x squared plus 1, all of that to the third power. So that is a composite function, right? So you think, okay, if this is some f of g of x here, then the inner function g of x would be x squared plus 1, and f of x would be x cubed. So that if I put in the g of x into the input of f, I would get exactly h of x. So something to keep in mind as we go through this example. And that's just what's said right down here, right? So we got our function f of x is x cubed and g of x is x squared plus 1, so that h of x is equal to f of g of x. And of course, what we're going to do here is we're going to differentiate it. So we don't know what the rule is yet of a derivative of a composite function. However, we do have previous established rules, in particular the power rule and the derivative of a sum of functions. So what we're going to do is we're going to expand the function h of x. So right up here again, right, the function x squared plus 1 quantity cubed, I can multiply that all out, and I'd have a polynomial function. I could differentiate it that way, and we can see what happens. So when we multiply the function out, we get this right here, the result. X to the 6th plus 3x to the 4th plus 3x squared plus 1. That is the exact same thing as our composite function h of x. And in case you didn't know, h of x is h of x. Don't know why that's there. All right, so then let's differentiate it. So if I differentiate this function, then I can just differentiate with respect to x term by term using the power rules. And the result is right down here, right? 6x to the 5th plus 12x cubed plus 6x. That's the derivative of our composite function h of x. And you say, well, how does f of x and g of x have anything to do this? Well, let's see. Now that I've differentiated it, I can rewrite it. I'll go ahead and take out the common factor from all the terms of 6x, and I get this result right down here at the bottom, 6x times the quantity x to the 4th plus 2x squared plus 1. And notice that this 4th degree polynomial right there being multiplied by 6x is the same thing as x squared plus 1 quantity squared. So we get that, all right, our derivative of our composite function h of x is really just the same as 6x times the quantity x squared plus 1 quantity squared. Now, some other things to notice here. I could actually rewrite that result as this right down here. And that is, well, you might be wondering why I'm doing this right now, but you'll see in a moment, 6x can technically be written as 2x times 3, right? Because 2x times 3 is 6x. So our derivative is the same as this result on the right, 2x times 3 times the quantity x squared plus 1 squared. That's our derivative. of our composite function. Now here's where we start going, Remember g of x. G of x was our inner function that we began with. Remember that h of x was the same thing as x squared plus 1 quantity cubed, remember. And our inner function g of x was the x squared plus 1. Now notice the derivative of that with respect to x is 2x. And we do see that sitting around there. Okay, derivative of g has something to do with this here. But what about f? Remember that f of x in our composite function was x cubed. The derivative of x cubed with respect to x is 3x squared. Now we don't see the 3x squared in particular sitting around in our derivative up here, but we do see the 3 and then stuff being squared. Now, to get around that, notice that if I take my derivative of my outer function f, which is x cubed, which we saw a moment ago is 3x squared, and I evaluate that at the inner function g of x, right here, I'm going to evaluate my derivative of the outer function at the inner function. So that's 3x squared, and then I replace the x with g, which is x squared plus 1, and we get this result right there. 3 times x squared plus 1 squared. Now we're starting to see it pieced together, right? Because up here, we had that 2x times 3 times x squared plus 1 quantity squared. That was our derivative of our composite function h of x. So here's my derivative right here, right? Also can be written like this, of the entire function. And what did we just show? Well, we showed that the derivative with respect to x of g of x, that's 2x, right? And then the derivative of f of x, the outer function evaluated at g of x, was 3 times x squared plus 1 quantity squared. And so hence the derivative of this composite function is exactly the derivative of g of x with respect to the input variable x times the derivative of the outer function with respect to x evaluated at the inner function. And like I said, what's going on here? Could this be true for all such functions for which this is defined? And that's what we're about to show, in fact. So we might hypothesize this is true or conjecture that it's true. So we're gonna go ahead and prove it. At least the part of the proof is going to be given here. Let's suppose that the function f of x is differentiable at g of a. Okay, so just replace x with g of a, or we can call that w, right? So just think, okay, my function f is differentiable, and I plug in this number g, evaluate at some location a, and that all works out. And then the function g is differentiable at the input variable for x equal to a. So we're assuming everything is nice and differentiable here. And then let's consider the general case of the composite function h of x. Let's call it f of g of x. So by definition of a derivative, right, evaluated at a location a, we can say that h prime of a here is the same as, of course, the derivative of the function f of g of x with respect to x evaluated at a. And so by definition, remember the limit definition, we had different forms. You go all the way back to the form where we had limit as x approaches a of h of x minus h of a divided by x minus a. That's definition of the derivative of h, right, at a. But of course, h is this composite function. So the derivative is really equivalent to this statement right here that I just circled. Limit as x goes to a of f of g of x minus f of g of a divided by x minus a. That's what it is by definition. Now, for the sake of this proof, okay, we're going to assume that g of a is not the same as g of x in general, at least for values of x near a but not equal to a. because in that case, there's another special case that we have to consider. So consider this a proof that works for most functions. But then if that happened to be true, you'd have to do another kind of side proof to consider that special situation. So then what are we going to do? We're going to pull a trick, if you will, and we're going to multiply our derivative by definition by 1, but of the form g of x minus g of a divided by g of x minus g of a, where we're going to keep in mind, we're going to do some change of variables at some point, where we can let u be g of x and w be g of a. We actually assumed w is g of a at the beginning, but now we're going to let u be equal to g of x. So what do we get? All right, here's our definition of the derivative so far that we had established of h at a, and now all you see I've done is just multiply that by 1. You can see that if g of x was equal to g of a near values of a, then we'd be multiplying by 0 over 0, and that's partly why this proof is specific for cases not in that situation. So then all I'm doing in this next step here, right, this is still my derivative, is I'm just taking the denominators here, x minus a and g of x minus g of a, and I'm flip-flopping them where they located. Right down here, I can do that because it's a product, right? The order of the product in the denominator does not matter. So that's what I did in that step. And then, remember, we were calling g of x equal to u and g of a equal to w. So then I just replace both of these in terms of u and w, like so. So that's where we're at. This derivative, h prime of a, is equal to this stuff where we're at. Now, remember at the very beginning, we are assuming g is differentiable at a. And because g is differentiable at a, we also know that g is continuous at a. And thus the limit as x goes to a of g of x should be equal to g of a. We're also assuming that f is differentiable at g of a, right? Those were all assumptions at the beginning. So it follows that as x goes to a, which is exactly what our limit is doing right there, right? Then u should approach w, because u is g of x and w is g of a. So this is g of x approaching g of a there for that reason. And so we can now rewrite this. So here's where we were. G of x is u. G of a is w, right? I'm just replacing the g of x and g of a in terms of their variables u and w. But notice that right here, this is the same as f prime of w. Remember, as x was approaching a, we showed that u was approaching w. And then, because, of course, we're in part assuming this derivative should exist, well, the limit of a product is the product of the limits, and notice that, oh, we can write this as this product. Limit as u goes to w of f of u minus f of w divided by u minus w times the limit as x goes to a of g of x minus g of a over x minus a. So the first limit is the same thing as f prime of w by definition. The second limit is the same thing as g prime of a by definition. So we get this product, but remember that w was what we were calling g of a. So really, this derivative here, which is h prime of a, is the same as f prime of g of a times g prime of a. And that's exactly what we were hypothesizing would be the case after we had done that initial example. And so this really does prove what we need to, this general case. And it gives us the chain rule. This is what the chain rule actually is. So the chain rule, okay, very, very important rule in our calculus discussion. If we suppose that h of x is equal to f of g of x, and g is differentiable at x, and f is differentiable at g of x, then the derivative of this composite function, h of x here, same thing as this, is as we just established, f prime of g of x times g prime of x. That is our chain rule. It gives us the general derivative of a composite function. Now, sometimes it's convenient to use Leibniz notation. And so an alternative way of writing this exact same thing is if we let u be g of x, then the function y is equal to h of x, which of course is f of g of x, is the same as f of u, right? Because I just replaced g of x with u. So then how would I interpret the result that's boxed in above in terms of Leibniz notation? Well, dy dx, which is our derivative of the function with respect to x, would be the function y differentiated with respect to u now, right? So it's the derivative of f, but with respect to g of x, really, right, is what that's saying, because we're calling g of x u. That's exactly that right there, right? So think of this first piece, that's your dy du, times, okay, the derivative of g with respect to x, but g is in this situation what we're calling u. Excuse me. So that's the same as du dx, right? So times a du dx, which is exactly what we see right here. Now, you see there's this pattern with the du's appearing in the denominator and numerators of these Leibniz notation. Of course, we cannot cancel those. These are not like fractions per se, right? They're notation to denote the concept of a derivative. But it is kind of a way to keep track if we're doing the chain rule correctly. We should see that pattern appear because the g, the inner function, needs to be differentiated with respect to the input variable x, right? That's our du dx, but then times the derivative of the outer function with respect to the inner function g, which is what we're calling u. So that's really it for this one. The goal of this video was to come up with the chain rule, which we did. And so after we've seen this, the next thing we do is look at some examples. So the next video is just going to be, let's just look at like a handful of derivatives using the chain rule and get a grip on how it works. And then we'll move on from there. So that is it for this video. This is Math and Beats, and I'm out.